Okay, good morning, everybody. So we're now into the next notebook, which is the Bitwise operations. And so this notebook hopefully explains why I bothered talking about the 2's complement representation of integers. The reason is that in C, you can actually perform operations on individual bits in a value. Not just integers, as it turns out, but for our purposes, we're going to stick with just integers. All right, so it is possible to operate on bits in your on a modern computer. So in other words, you can actually go in and given a value, you can actually fiddle with the bits in the value, which causes the values in the the value of the value that you're fiddling the bits in to change. You don't normally do this. Well, you wouldn't have done it in 121 or 124. But it turns out that when you're programming in C in some applications, this is a useful thing to do, especially if you're programming in an environment that has constrained memory or constrained processing. So you can actually store true-false values in an individual bit, whereas if you're working in a language like Java or Python, true-false values are stored using many more than one bit, right? Probably, actually I don't know how many bits are used to store a Boolean value in those languages, but it's a lot more than one. All right, so C does offer you the ability to operate on individual bits, but your computer does not let you access an individual bit. So in other words, there's probably no way in a modern computer to go in and ask for a particular bit somewhere in memory. You have to do something else. You have to get a bunch of bits, and then you have to operate on the bit that you want after you get the bunch. But that's a discussion for your architecture course, maybe. Okay, so it turns out that if you know how to fiddle with bits, you can do a whole bunch of clever things very fast, which isn't terribly useful in today's world on a desktop computer anyway, unless you're working in an area where speed is of absolute importance. So in something like a video game or in video rendering or some scientific applications, the stuff that I talk about today might find application. For most programmers though, they're not really going to work with the individual, but with bitwise operations. It used to be taught, so many years ago, we used to teach you this sort of stuff, but it's kind of fallen out of favor. Fortunately, there are 2 very good references that actually talk about this stuff. So one is by Knuth. This is Donald Knuth is a very famous computer scientist and mathematician. He wrote a series of books called The Art of Computer Programming. One of these books deals with bitwise operations. Well, part of one of these books deals with bitwise operations. The second book here by Warren is an entire book that deals with bitwise operations. So it's something like 400 or 500 pages. And he gets up to all sorts of nonsense twiddling with bits. If you're interested in this sort of thing, I recommend you take a look at probably the second reference first. Knuth is harder to read, I think. All right, so in this course, we're not going to look in great detail at these operations, but we will look at some. Okay, so to make this understandable, I have to be able to print out a binary number. And C doesn't make this easy to do, right? So there's no way that you can, given an int, just print out a binary number easily in C. So I have to write a function that does it for us. And so that print B prints a binary number. So uint 8 underscore t, that is a type defined in, I think, types.h, which is an unsigned integer value occupying 8 bits, right? So there is a type that you can use for that. So print B will print out an 8-bit unsigned integer number in its binary representation. Right? Obviously, if you look at this thing here, you probably won't be able to understand how it works by the end of this lecture or the next, or by the end of this notebook anyway. You should be able to look at that code and figure out exactly what is happening in this code. Right? Okay. So what are your individual bitwise operations, right? So remember, you're operating on values that are 0 and 1. So the easiest way to think about, or one way to think about this, is to think about operating on values that are true and false. So your logical operators, so not, and or, they all have corresponding bitwise operations, right? So bitwise not. So if you have this 1 bit, the value is 0 or 1, then not or complement flips the value of the bit, right? So 0 becomes 1, 1 becomes 0. Right? So if x is 0, not x is 1. If x is 1, not x is 0, right? So if x is true, false, not x is true, right? If x is true, not x is false. So if you have an integer value in C, the twiddle operator or the tilde operator is bitwise not, right? So y equals tilde x is the bitwise not of x. Right? Any bit in x that's a 0 gets turned into a 1. Any bit in y, y becomes equal to the not of x. Right? So any bit in x that is 1 becomes 0 in y. Any bit that is 0 in x becomes 1 in y. Right? So if that's x, right, the value of not x or y becomes that right there. Right? Zeros become ones, ones become zeros. Taking the bitwise not of a value is equivalent to the ones. Oh, right. If you know what ones complement is, then the bitwise not of a value is equivalent to the ones complement of the value. Right? So there's bitwise not, right? Bitwise and is like logical and, right? So if you have two bits x and y, then and or conjunction, if you're a mathematician, yields a bit whose value is 1 if and only if both x and y are also 1. Right? So in this table here, we've got x and y, 1 and 1, then the and of those two bits is 1, anything else is 0. Right? And this is the same thing as treating these as true and false. Right? True and true is true. Right? True and anything else is false, which is the other three rows of the table. So if you want bitwise and, that's what the single ampersand is for. Right? Remember the double ampersand is C's and Java's logical and operator. Right? In both C and Java, and is the single ampersand is the bitwise and operator. Right? So if you take the and of two values, right, you just combine the bits. Anytime you see two bits that are both 1, you get a 1. Every other combination of bits, you get a 0. So here if we take the and of x and y, you get all zeros except for that one column where both values are 1. Where is the hint? Sorry. What's going on here? Oh, there's some code here. Okay, right. So I brought the wrong computer with me, and so I'm using an incorrectly installed version of Jupyter. So you're going to get this. You might see this on a Mac too. I think if anybody using this on a Mac, or if you've recently installed Anaconda, you're going to get this nonsense here. So I have to figure out how to fix this, but I don't know what's going on. You're getting a warning caused by the the C kernel that I'm using. So you have to ignore all this pink stuff and then look at the output down here. So this is computing the not of x, right? If you go back and look at the code, there's our value there, right? So it turns out 1001010 is 18, right? If you take its not, you end up with the bit pattern that was shown above, right? So zeros become ones, ones become zeros. Okay, so sorry, I have to go back. I don't know why it hid all these. Anyway, so on a modern computer, the representation of a integer is probably 2's complement, right? So if you have a signed value and you take its not, the value of not x is equal to the negative x is equal to the 1's complement of x plus 1. Right, which is what I showed you in the last lecture. Right, you want to compute the negative value. You will have a value x, and you want to compute its negative value. You take its 1's complement, right? Flip all the bits, and then add 1. Right. Well, we know how to flip all the bits. Right. That's just not x. Adding 1 is easy. You just add 1. Right. And so what happens? So if you start out with an with a signed integer value, so we know it's 2's complement. Right. Take its not and add 1. And print it out, you end up getting a mess probably, because I'm going to get the warning again. Yes. Whoop. Oh, and I don't. Oh, there it is. Right. So if x starts out as 99, after you do the not of x and add 1 to it, you get minus 99, right? Which was exactly the result from the previous lecture. Okay, so for and, we're going to do the same thing. So I'm going to make x and y. So 18 and 206. Right. Those have the bit patterns that were shown earlier in the notebook. Right? We're going to compute the and, right, as z, which is x and y, and then we're going to print out all the values. So there's x, right, and there's y. right? Take their and you get that value down there. Okay, so if you have a bit x, then the following must be true, right? If you take x and 0, right? Remember, anything and 0 is always 0, right? So anything and false is always false, right? X and 1 is always equal to x, right? So in other words, if x is 1, 1 and 1 is 1, right? If x is 0, then 0 and 1 is 0, right? And so that turns out to be a very useful thing to remember if you're into fiddling with bits, right? So using a pattern of bits called a mask, right? You can actually select subsets of bits from an integer value using this property right here, right? So if you want to pull out a set of bits from some value, right? What you do is you create some value x, right? Where the bits are equal to 1. Sorry. You create a mask whose values are all 1, where you want to select the bit from x, right? Because of this property here, right? Taking the and with 1 gives you the corresponding value in x. So here is my value x, right? I can make a mask equal to all zeros and a 1, right? And that will select that bit right there, right? And it'll cause all the other bits to become 0, right? So when you apply this mask to x using the and operator, right, you end up with all zeros here, right? I'm only selecting that bit from x, right? Because the 1 in the mask is there, right? So if x is, we can select the least significant bit from x. So this is pulling out the rightmost bit of x, right? Oops, sorry. Right, so notice we get a 0 here in our rightmost bit, right? Also notice that the value of x is even here, it's 18, right? If you have an odd number, right, in this case 19, right, that bit must be 1. Right? It has to be 1 because the value of that, when you convert that bit to decimal, it's equal to the number 1. Right? So you're going to add 1 to some other positive number, so that makes the value of x odd. Right? And so if you select the last bit and it's a 1, you know that the number is odd. Right? If you select the last bit and the number is 0, you know that the number is even. Right? And it turns out this provides an efficient way to determine if an integer value is odd or even. Right? You simply apply the mask. The mask is just equal to 1, right? It doesn't matter how big your binary number is. That's equal to the decimal value 1. So it's easy to make this mask, right? So here's is odd, right? It takes in some value x, right? And it simply computes the and of x and 1, right? All of the most significant bits, except for the last bit, right? Or all of the bits except for the least significant bit become 0 in the result, right? And the last bit in the number corresponds to the value of the least significant bit. So if it's 1, you know it's odd. If it's 0, you know it's even. Right? So here we're going to try -2. See what happens. We get a bunch of stuff, and where's my output? There it is. So -2 is even, right? Change the 2 to something else, so -3. Run that. -3 is odd, right? And try positive values, of course. So 39, right? And that's also going to be odd, right? So playing this, so it turns out that applying a mask to an integer value like this turns out to be a very useful thing once you start playing around with these bitwise operators, right? It's often very useful to go in and extract the bits that you want from a value that you've computed. Okay, bitwise OR. Well, bitwise OR is like logical OR, right? So if you have 2 bits x and y, and either one is a 1, then the result is also 1, right? So in other words, if both values are 0, then x or y is 0. Right? So false and false is false. Sorry, false or false is false, right? True or anything is always true. So you get 1s here, right? Not surprisingly, right? The vertical bar is C's and Java's bitwise OR operator, right? So if you take the OR of x and y here, right? Anywhere you see a 1 in either number, you're going to get a 1 in the result, right? So there's a 1 here, you get a 1 here. There's a 1 there, you get a 1 there, and so on and so on and so forth, right? The only place you get a 0 is where there are 2 zeros, right? So there and there, and here and here, right? Again, you can run this little piece of code here. All it does is take 2 values x and y and then compute the OR here, right? If you run this, you're going to get the exact same result that's up here. Okay, so just like with the AND operator, there is an identity here involving the OR operator, right? So XOR 1 is always 1, right? Anything and 1 is always, any value OR true is always true, right? XOR 0 is always equal to x, right? So if x is 0, XOR, so false or false is false, right? If x is 1, true or false is equal to true. Right? And so again, you can apply a mask, but this time you can use the OR operator instead of using AND. Right? So using a mask, you can ensure that a subset of bits from an integer value x are equal to, sorry. Right? So if you use a mask, oh, come on. Sorry, the Mac is new and I don't normally use a Mac. Oh, it's doing it again. Oh, never mind. Okay, so using a mask and the OR operator, you can ensure that a subset of bits from an integer value x are always equal to 1, and you leave the remaining bits unchanged. Right? So this lets you set a range of bits to 1 and leave the other bits unaffected. Right? So for example, if I want to flip the least significant bit, right, I can write a mask whose value is equal to 1, right, and now I can use OR. Right? So XOR the mask, right, because I've set that bit to 1, that's going to guarantee that when I take the OR, this is a 1, right? All the other values are 0, so XOR 0 is equal to x, right? And so that leaves all of these other bits unchanged. Right? So when you take the OR of 18 and 1, you get 19. Right? So it lets me flip that. It lets me flip the least significant bit here. Right? If the least significant bit's already 1, then the operation doesn't do anything. Right? So here's the value 19. Right? Its least significant bit is 1. 1 or 1 is 1. Right? Anything or 0 is the anything. Right? And so you get all that back. Right? So that lets me flip a positive number to the next largest negative number. And you might say, well, that's not super useful, and you're right, right? But instead of flipping just the least significant bit, you can flip any bit you want, right? You can turn it to 1, sorry, not flip. You can, instead of, you can set any bit you want to 1 by using this trick, right? So if I want to set the bit corresponding to 2 to the power 5, right, which is equal to 32, right, I can flip that corresponding bit by writing XOR 32. Right? So remember, all of your bits correspond to a power of 2. Right? The least significant bit corresponds to 2 to the 0. Right? The second bit from the right is 2 to the 1. Right? The third bit from the right is 2 squared, and so on and so on and so forth. Right? So this is the 6th bit, I guess, from the right. And it turns out you can play a really stupid trick using this using this technique. Right? It turns out you can flip uppercase letters to lowercase letters with this trick. So here I've got a string made up of all the uppercase letters. Right? I'm going to print out the string, and then I'm going to iterate over the characters of the string. Right? So I'm going to pull out one character at a time. I know that's an uppercase letter. Right? I'm going to take that letter C and take the and compute the OR with 32. Right? And I claim that produces the corresponding lowercase letter. Right? Let's see if this works. Get a bunch of stuff, and there we go. Right? So there's our original uppercase string. Right? That's the result of applying OR 32 to every character in the string. Right? It actually changes it. It actually changes the uppercase letters to lowercase letters. Right? Now the reason this works is because of the way that the English letters, it's caused because of the way that the characters on my computer are encoded. It's probably the same on your computer as well, unless you're using a different language from English. Right? So it turns out that the difference between a and little a happens to be equal to a power of 32, which is funny. And that's the reason why this works. Right? If you actually look at the ASCII table for the English letters, you'll see that these are offset exactly by a power of 2. And so flipping or changing the bit causes the case to go from uppercase to lowercase. Right? You might want to go the other way, which is what exclusive OR is for. Right? The other way, or you might want to flip, so from uppercase to lowercase or lowercase to uppercase. And that's what exclusive OR is for. You normally don't get taught what exclusive OR is in 121 or 124. Right? Exclusive OR is the version of OR where you get 1 if and only if exactly one of the two values is 1. Right? So 1 exclusive OR 0 is 1. Right? 0 XOR 1 is 1. Right? If both bits have the same value, then you get 0. Right? Which is why it's called exclusive OR. Right? Exactly one of the two values has to be 1. So the binary operator, that's the caret. So shift 6 on most keyboards is exclusive OR. Right? So this only works if x and y are both they both have the same integer type. Right? So there's x, there's y. Right? Anywhere you see exactly 1, 1 in a column, you get a 1. Right? Anywhere you see 2 zeros, you get a 0. And anywhere you see 2 1s, there and there, you also get a 0. Right? So again, here's if you run this code here, it's going to compute the exclusive OR of, these two values here, right? And you'll get the that result printed out. Okay, so there is also an identity for exclusive OR. Right? X XOR 0 is always equal to x. Right? So if x is 1, right? 1 XOR 0 is 1. If x is 0, 0 XOR 0 is 0. Right? And XOR 1 is equal to the not of x. Right? So in other words, if you take the exclusive OR with 1, you always flip the value of x. Right? So 1 exclusive OR 1, they're both 1, so that becomes 0. Right? 0 XOR 1 is 1, right? Because exactly one of the two values is 1. Right? And so now if you use a mask and you use XOR to apply the mask, you can toggle the value of a bit. Right? So zeros become 1s and 1s become 0s. So here if my mask is a 1, right, I can flip that 0 to a 1 if I take the XOR of x in the mask. Right? Similarly, if this bit's a 1, and that's my mask, right, when I apply the mask using XOR, right, that toggles the value of that bit. Right? It leaves all the other ones unchanged, right, because x exclusive OR 0 is always equal to x. Right? So anywhere where the mask is 0 leaves the value of leaves the bits in x unchanged. Right? And so now, again, using the same example as before, where I have the uppercase letters, right, and the lowercase letters now, right? If you take the exclusive OR of a character, or one of these characters in these strings, right, with 32, it turns out that flips the case of the letter. Right? So if you run that, right? So if I start out with that string there, if I start out with this string here, right? I take each letter of the string, compute the XOR with 32, that converts everything to lowercase. Right? If you start out with all lowercase letters, you compute the XOR of each character with 32, that becomes all uppercase letters. Right? And all that's happening here is that you're flipping the value of one of the bits in the number. Right? And that does your conversion from upper to lowercase. Right? It only works with the letters. It doesn't work with any other characters in the ASCII in this encoding. Right? Okay, so those are your basic operations. They're the same as all of your basic logical operations. Okay, so given a bunch of bits, what else can you do with them, right? And so it turns out the other thing that you can do with them is that you can move them around. Right? So you can shift bits left and right. Right? So in other words, I can take the bits of a number, I can move them all over one position to the left, or I can take the bits of the number and move them all one position to the right. Or more generally, you can move them all k positions to the left or k positions to the right. Right? Okay, so if you want to shift bits in C, that value that you're shifting by has to be positive or 0, right? So you can shift by 0, which does nothing, right? You can shift by 1, which moves all the bits one direction, left or right. You're not allowed to shift by a negative value, right? If you try to do that, the result is undefined behavior in C. So you might get something might happen, but you don't know what's going to happen, right? Also, if you're trying to shift the bits of a number, there's a limit in how many positions you can shift the bits. So if you have an 8-bit number, you're only supposed to shift by at most 7 bits, I think. And if you have a 32-bit number, you're only supposed to shift by at most 31 bits. Again, if you try to shift by more, undefined behavior. Okay, so there's 2 types of shifts because of the fact that 2's complement exists. Right? So if you have an unsigned value, then shifting bits does exactly what you probably imagine it will do, right? It moves the bits and that's it, right? So if I shift to the left, the bits all shift to the left, right? Anything on the left-hand side of the number just falls off the front of the number. But you have to remember that in 2's complement, the value of that leftmost bit is important, right? If it's a 1, it's negative. So if you left shift a signed number, what happens to the signed bit, right? If it falls off the end, what happens to the sign of your number? Does it become positive? Does it stay negative? Right? That's why there's a difference. Right? So your arithmetic shift deals with the cases where you are shifting a signed value. Right? It would be nice that if you shifted a signed value and overflow doesn't occur, the sign of the number stays the same. Right? So in other words, if you shift a negative number 1 bit to the left, right? In many cases, it would be nice if the number stayed negative. Right, assuming overflow doesn't occur. Okay, so shifting left. All right, so I've got a sequence of bits, right? 0s and 1s, right? You know how to calculate the value of x in decimal, right? You know that each bit is just multiplied by some power of 2, right? So the rightmost bit is multiplied by 2 to the 0, right? The b, I guess n in this case, is multiplied by 2 to the 1. Right? The first bit multiplied by 2 to the n minus 1. Right? Okay, so what happens if I stick a bunch of zeros onto the end of the number? Right? So I'm going to tack k zeros or k bits onto the end. Right? I'm not going to lose any of the bits in the number right now. So here are all my bits. Right? I add k zeros to the end of the number. Right? So what happens when I compute the decimal value of y? Right? So if you work out the math, right, your first bit gets multiplied by 2 to the k, just like before, 2 to the n minus 1, just like before, right? But you also have to add in k, right? So the leftmost bit gets multiplied by 2 to the k plus n minus 1, right? The second bit gets multiplied by 2 to the n minus 2, but you have to take into account you added k zeros to the n. So it's k plus n minus 2. And so on and so on and so on and so on, right? If you simplify this all down, right, you'll realize that you get back the original number x multiplied by 2 to the k, right? So if I add 1 0 to the end of the number, that's like multiplying the number by 2, right? Multiplies by 2 to the 1, right? If I add 2 zeros to the end of the number, that's like multiplying by 4, right? If I add 3 zeros to the end of the number, that's like multiplying by 8, and so on and so on and so forth, right? And this is exactly what happens, it's exactly analogous to what happens if you start sticking zeros onto the end of a base 10 number, right? So I start out with 1, I add a 0 to the end, it becomes 10, right? I add 2 zeros to the end, it becomes 100. I add 3 zeros to the end, it becomes 1,000, right? You're simply multiplying the number by some power of 10, right? So shifting the digits of a binary number, k positions to the left, is sort of like adding k zeros to the end of the number, right? The problem is that you have to end up with a binary number that has the same number of bits as what you started with, right? And so the bits at the front of the number just fall off the front of the number, right? And so that's called a left shift. So a left shift of an unsigned number essentially is multiplying by some power of 2, right? You left shift by 1 bit, that's like multiplying by 2, right? You left shift 2 bits, it's like multiplying by 4, right? And so on and so on and so forth. Right, so it turns out multiplying or dividing by a power of 2 is very efficient on a modern CPU because a modern CPU can shift the bits in the number relatively easily, right, or very efficiently. Okay, so a left shift moves the bits in the direction of the most significant bit, right? So it moves them to the left. That's why it's called a left shift. But it's only a left shift if you write your bits in the order that we write them in, right? From most significant to least significant. Okay, so if you any of the bits on the left-hand side of the number, they fall off the front of the number, right? The values on the right-hand side of the number, zeros get shifted in for the values on the right. Right, and so there's a picture of a logical left shift. Right, so this is not arithmetic, right? So in an arithmetic left shift, you want to try to preserve the sign of the number. Here you can see the sign of the number clearly changes, right? It was 1, it now becomes 0. So this is a logical shift, right? Logical shift, the bits just move, and you don't care about the sign bit. Right, so this is a shift of 2 bits. So every bit's going to move 2 positions to the left, right? So that 1 moves 1, 2 positions over here, right? So it falls off the front of the number. This one moves 1, 2. Falls off the front of the number. That 0 moves 1, 2, so it becomes the first bit now. Right? That 1 shifts 1, 2 positions to the left, ends up over here. Anything over here, you just assume is 0, and so you get a bunch of zeros being shifted in over here. Right? And so there's your picture of a logical left shift. Right? Okay, so what happens if this bit's important? Right? So if that bit, so in other words, if this bit is, is the signed bit in a 2's complement number, right? So in a signed, if this is a signed number, you want to preserve the value of this bit if you can, right? And so that's called an arithmetic left shift, right? So if no overflow occurs, right, then in an arithmetic left shift, shifting the bits by k positions to the left is exactly like multiplying the value by 2 to the k, right? So that's what you want to happen. Unfortunately, because there are multiple representations of signed numbers, right? We're using 2's complement, but there are other versions of signed numbers, right? You don't actually know what the exact bit pattern is going to be, right? You have to know what is your computer representing the signed numbers as. Right? Is it 1's complement? Is it 2's complement? Is it some sort of sign bit representation? And then you can figure out what the arithmetic left shift value is. Right? So if you're using 2's complement, which is what we're assuming, right? Then an arithmetic left shift is identical to a logical left shift. So the exact same thing happens, right? But you try to preserve the value of the most significant bit. Right? So what does C's left shift operator do? Right. So in C, the left shift operator is less than, right? No space in between. Right. And so this shifts k positions to the left. Right. So x less than k produces the value where x has its bits shifted k positions to the left. Right. So that's stored in y. X doesn't change, right? So it's the same as adding 2 values. The value of the operands doesn't change. Okay, so it turns out if k is negative, the result is undefined, right? If k is greater than or equal to the number of bits in x, the result is also undefined, right? For unsigned types, the value of the left shift is well defined for unsigned types, the value of the left shift is just the logical left shift, right? All the bits move k positions to the left, zeros come in on the right. The problem is with the signed types. So you shift a signed number to the left, behavior is undefined, right? So if overflow does not occur, then in C, the value is guaranteed to be equal to multiplying the number by 2 to the k, right? Sign doesn't change, right? If overflow occurs, anything is allowed to happen. Okay, so here is shifting 23 bits to the 1, 2, 3, 4, and so on positions to the left. So we'll run that, and something will come out eventually. Here we go. Okay, so x starts out as 23, right? We compute the value of shifting the bits of x 1 position to the left, right? And so what's the easiest way to do this? So that 1 moves to here, right? The second one moves to here, the third one moves to here, right? And so on and so on and so forth, right? If you crunch out the decimal value of that number, you can convince yourself it's equal to 46, right? Okay, take the 23, shift the bits 2 positions to the left, right? You get that, right? Shift them 3 positions to the left, you get that. Oh, sorry, that. Right, now remember, we're working with an unsigned value here, right? So when you compute the value of this number, it's 184, right? It's not negative in this case because we're assuming unsigned values here, right? But notice that if this was a signed value, and if C actually performed the shift this way in an arithmetic shift, this would suddenly become negative, right? So if you had a signed 92, shift 1 position to the left, suddenly it becomes a negative value, right? Because that first bit is now 1, right? If you shift again, right, I now end up with this pattern here, right? So the most significant bit has gone from a 1 to a 0, so the magnitude of the number actually decreases, right? This is exactly what happens when a number overflows, right? So when an integer value overflows, something funny is happening on the left-hand side of the number, right? Here, that 1 has fallen off the front, right? And that results in a smaller number than what you started with, right? 112 is less than 184, right? Even though you're shifting the bits 1 position to the left, right? Okay, so what happens if you shift the signed value? So what's going to happen here depends on your computer. I think on most of your desktop computers, you'll get the same result. So here we start out with a negative number, right? So the most significant bit is a 1, right? I'm going to start shifting bits to the left, right? So you shift 1 bit to the left, you get that pattern there. Now, the confusing part here is that you don't know, right? Is the result 1, 1, 1 because that 1 moved to here? Or did your computer actually try to preserve that signed bit here, right? So it turns out your computer is trying to preserve that signed bit. Shift again, you get that. Right, shift 1 more time, you get that. Right, now when you shift again, right, so in this particular case, that 1 falls off the end and you end up with this pattern here. Right, so in other words, a logical shift has occurred, you've lost the value of the signed bit. Right, so why has that happened? Because you can't, minus 240 doesn't exist in an 8-bit signed number. Right, and so that again is overflow. Right, you've overflowed to the positive side and gotten 16. So it looks like on my computer, it's simply performing a logical left shift every time. Sorry, it's simply performing, so when overflow occurs, it's like a logical left shift has occurred. Right. Okay, so shifting left is like multiplying by a power of 2. Right. Shifting right, not surprisingly, is like dividing by a power of 2. Right, so you can go through this exercise again. I'm not going to do this in the lecture, right? You start out with a bunch of bits, right? And now you, we're going to do the divide by 2 in binary, right? So that's what the rest of the notebook talks about. It's not important that you understand the details in here, right? What's going on here, though, is that when you right shift by a power of 2, it's like dividing by when you right shift by k bits, it's like dividing by a power of 2. So take the number x, divide it by 2 to the k, and take the floor. Right? So that's the mathematical floor if you know what that means. Right? The floor rounds towards 0. Right? And so this is like taking a base 10 number and just throwing away the digits at the end. Right? So if you start out with 11 and throw away the rightmost 1, you get 1. That's like dividing by 10. Right? 11 divided by 10 is 1 with some remainder. Throw away the remainder. Right? So right shift of k bits is similar to floor division by 2 to the k. Right? So you divide by 2 to the k, take the floor. So logical right shift, what happens? Well, the bits just move k positions to the right. Right? The bits on the right-hand side of the number just go away. So that 1, if you shift this number by 2 bits to the right, that 1 goes away. That 1 goes away, that 0 ends up in the least significant bit of the value. Right? On the right-hand side, for a logical shift, zeros get shifted in from the right. Right? So that 1 goes to here, and a 0 comes in here and here. Okay, so what about an arithmetic right shift? So again, assuming no overflow occurs, right, the shifted value is equal to x divided by 2 to the k, or multiplied by 2 to the minus k. Right, again, because multiple representations of signed numbers exist, you don't know what the exact bit pattern is. Right, but if you're working in 2's complement, right, what happens is the following. Right, so here I'm going to shift this number 2 bits to the right. Right, and now our number is a signed number. We're assuming 2's complement representation. Right, so that 1 falls off the end, that 1 falls off the end. All the other bits, except for the leftmost bit, move over 2 positions to the right. Right, so that 1 ends up over here. Yes, that 1 ends up over here. The sign bit shifts. Right. Any of the other the bits coming in from the right, they are just copies of the signed bit. Right. So instead of shifting in zeros from here, you're going to take this value here, copy it into here and here. Do I have a, yeah, here's a better way. Here's a better example. So for a negative number, right, if you do an arithmetic right shift, that 1 gets copied into here or here, and that 1 there preserves the sign of the number. Right. I claim that if you do this, you do in fact get that original value divided by 2 to the k, divided by 4 in this case. Right. So here, that original number is minus 45. Right. If you compute the value of this number here, it's minus 12, right? Minus 45 divided by 4 is minus 11 and a bit, but you have to remember this rounds, this is floor. Sorry, floor rounds to minus infinity, right? So minus 11 and a bit rounds to minus 12 if you use the floor operation, right? You have to be careful with this, right? Because in Java and in C, division is actually truncating division. So minus 45 divided by 4 in C becomes minus 11, right? But if you're shifting the bits, it becomes minus 12. You're rounding towards minus infinity, right? Oh, actually, I even tell you right here, right? It's not the same result as dividing by 4 in C or in Java. Okay, so the right shift operator in C is just the double, is just greater than. It has all of the same requirements as with left shifting, right? You can't shift by a negative number of bits. You can't shift by more bits than there are in the number. For the unsigned types, the value of a right shift is always a logical right shift, right? So you just shift the bits to the right, zeros come in from the left. Okay, so the problem with the right shift operator is that the C standard says the result is undefined, right? Well, it says the result is implementation dependent if a negative value is shifted. So what this is trying to tell you is the C language doesn't guarantee what happens if you right shift a signed integer value. Right? You might get the sign, it might be an arithmetic shift, it might not be. Right? And so you're not supposed to right shift a signed value. Right? Because you cannot predict the result. So again, the same illustration as before. We're just going to take a number and shift it a bunch of bits to the right. Here we go. Right. So starting out with 23, shift the bits 1 position to the right. Right. That's like dividing by 2, so that you get 11. Right. Take 11, shift it 1 bit to the right. That's like dividing by 2, so you get a 5. Right, and so on and so on and so forth. If you shift the signed value, it does work on my computer. You do get a predictable result on my computer. You're not guaranteed to get a predictable result on every computer, right? So in other words, if I took this code and ran it on someone else's computer, probably someone else's unusual architecture computer, you might get a different result, right? So minus 15 divided by 2 is minus 7 and a bit, 7.5, right? Round towards minus infinity, you get minus 8, right? Notice that the sign bit is being replicated as you shift to the right, right? So as we shift to the right, it's not zeros coming in, right? The sign bit is being maintained, right? Which preserves the sign of our number. All right, so there is the introduction to the bitwise operators in C. The next notebook actually does an example of why you might want to use these operators in C. But I will leave that for, I guess, Tuesday, Thursday. So Thursday is your test. So I guess next week we'll talk about the examples of where you might want to apply these these bitwise operators. All right, if you haven't seen the announcement, I have to travel again today, so I don't have office hours today, but I will be here, well, I'm supposed to be here tomorrow, assuming I don't get stuck in traffic. So if you have any last minute questions for the test, tomorrow's office hours would be the time to come ask. Any other questions about the test while I'm here? Anybody? All right.